Guilty as anybody. And us paleontologists have butterfingers.
Huh.
That's more common than most people are willing to acknowledge. But let's be honest, we've all broken fossils in the
Yes.
lab, in the field. That's exactly one of the beauties of 3D. This is the future, but now.
He did something that I dreamed someone would do, and that is Dr. Dan Vidal. He wrote the book on modern day photogrammetry using technology with my beloved sauropods. Thank you for the paper that just dropped the other day on your sauropods where you talk about their mating.
Aside from science, I also like whipcraft.
Okay.
So I know my way around whips a lot. Well, that was very humbling. I'm I'm speechless, and that really blew my mind back then.
In this episode of Fossil Crates Live, I sit down with Dr. Daniel Vidal to explore how photogrammetry is transforming paleontology and how we can actually test ideas about dinosaur behavior, including how giant sauropods mated. Make sure to watch to the end, as yours truly from 1997 makes an amazing, glorious appearance. Just wait. And if you haven't already subscribed, please do for more real paleontology.
We have with us an amazing guest, none other than Dr. Dan Vidal, who is a postdoc at the University of Chicago. But more importantly to me, he wrote the book on modern day photogrammetry using technology with my beloved sauropods. Behind me are some images that from his most recent giraffe paper, and he did something that I dreamed someone would do, and that is he took software and took modern animals that we can actually look at and then showed the software replicates it. And then he moved forward and started doing sauropod work. So incredible scientific method from making sure it works and moving. Incredibly smart. Future, if you're looking to do paleo and you're like technology, this is the gentleman you should be following. So, Dr. Vidal, if I may call you Dan, please tell us about your background, where are you from, etc.
Well, that was very humbling. I'm I'm speechless. Hello everybody. So originally I'm from Spain. My story is I have to tell my origins is kind of weird because I was born in London, then my parents went to Spain. That's where I lived most of my life, and so a little bit of my origin is that I was never. There's two type of paleontologists: those who fell in love with fossils and ancient life when they were kids, mostly dinosaurs, but some people also fall in love with mammoths, etc. So I was a dinosaur kid. Yeah, guilty as anybody. Um, and that led me to study a career in biology because I was more into living organisms than to rocks. Though I got my geology training crammed up along the way. And I know I'm one of those terrible students. I'm not suggesting anybody should be a terrible student, but I definitely was. My marks were like anything I liked, I had great marks. Anything I didn't like, either I failed or I got really average. That was until the very ending when I realized my grades were very important. So I got to study a lot. And basically, by the end of my master's, I became a very good student when it was no longer useful for me at all.
That's hilarious. So many people, they ask me, how can I become a paleontologist if my grades aren't great? So you're someone that I can point to that did it. They just had to improve their grades.
Yeah, you did it. It was hard because, especially when I come from Spain, funding for doing a PhD is very scarce. There's not a lot of jobs in paleo outside academia, like in the United States, for example. So there's no Black Hills Institute or any other or fossil crates where you can actually develop a career outside of academia. So basically, academia it is, and it's not that well founded. So I got a striking luck. I have something I call Vidal's luck. as dumb as it sounds, but I'm a very lucky person. I put a lot of hard work onto it, but I also have to acknowledge I've been terribly lucky. And my PhD grant, I got that after applying to a bunch of stuff which I got rejected from. This one, I was second. It was like my last shot, and the person who was before me got another grant, rejected it, so I got to do a PhD. That was
And the world is better for it. No offense to the other person, but I'm glad you got here. At least for sauropoddom, you have done an incredible job in a short amount of time. It doesn't feel short to you, but to me, it's just 1,000 days. To you, it's like 8 years of sweat and tears and a lot of pictures.
Yeah.
You may be the only person that has more paleo photos than me. I have almost 700,000 photos of paleontology, and I'm guessing with your photogrammetry, you get that on a couple sauropods.
Oh, whoa! Never done the math, but I have like a 5 terabyte external drive just full of pictures of sauropods and other stuff. But I mean, just for 3D, I mean.
Yeah, because you were Dr. Vidal shared with me some of his Haplocanthosaurus scans of the holotype of Haplo for a paper that we're working on. And what an incredibly cool experience. I had never touched Maya. I double click it, I open up your device, and all of a sudden I am flying around with no clue what I'm doing. I'm seeing Haplocanthosaurus elements coming to life on my screen. And it was amazing because my back didn't hurt. And I didn't worry about breaking it.
Exactly. That's exactly one of the beauties of 3D. And I can remember, so here's another thing about me. I really don't like talking about myself at all. It feels so egotistical to me, but when it's one of the things I am the most proud of. Most people don't get to choose their subject of thesis. Most people just, go around asking, oh, can I do this? Can I do that, to established researchers for a PhD? And in my case, I remember very vividly seeing a talk about Plateosaurus and virtual fossils by Heinrich Mallison.
Yes.
At an EAVP conference. And that really blew my mind back then. I really saw this is the future now. So essentially, I went with who were my advisors. I had done my undergrad thesis on Titanosaur osteoderms from Spain. So I went to my advisors, whom I knew had worked on this sauropod from Niger, Spinophorosaurus. I knew it was fairly complete. So I asked them, can I do for my master thesis what Heinrich did on Plateosaurus with Spinophoro? They agreed, and that just grew and grew and grew. While when I was doing my PhD, I got the very good luck again of having a travel grant awarded, which enabled me to visit the United States and the next year Argentina. This was within the first months of my PhD starting. So I got to visit all these American institutions and be able to study all this classic material, which for the better part of a century had received very little attention other than the monographs. So to me, that was a very firsthand experience. I got a lot of material, and that's how my thesis became, just Spinophorosaurus to all sauropods.
Well, your work is amazing. I thank you for the paper that just dropped the other day on your sauropods, where you talk about their mating as well as the overview of what your work has been. I thought it was really cool. And what I love about your work is how it pops visually. And I believe you have a presentation that you wanted to share with us. So I can't wait. The screen share is yours, my friend.
Okay. I will just make a comment about the visual thing. I believe we are essentially visual animals. And I always push myself to try and convey all the information I can through images and not text. Because text you have to process, whereas if you're seeing it, I think that's more intuitive and that's better to convey any ideas or whatever. So that's why I try to focus a lot on that. So if I may, I'm going to screen share.
Yes, please do. It is yours. The floor is yours.
So this is basically, can you see it?
Yes, what a beautiful PowerPoint. If you click, well, there you go.
So this is this is not exactly prepared for this session. I have to admit this is a retool of a talk I've been giving on and off for a long time, and I just realized this is the first time I'm going to talk about this in English because I just opened today this morning the PPT, to get some things in, some things out, and I realized, oh, this is in Spanish. Crap.
Está
So
bien, mi amigo. Está bien.
No, I had to basically translate everything. So excuse any typos or missing, Spanish bits here and there that might be all over the presentation. So, well, I have to change the Twitter logo. God damn it. This is where you can see this is an old talk. All right. So, as I said, I was a dinosaur kid, and as a dinosaur kid from my generation, I was born in 1989. So, Jurassic Park was the thing that, for a lot of us, got hooked us into paleontology. And to me, Jurassic Park has a big quality aside from making dinosaurs even more popular to all kids and fostering many careers for a lot of people in paleontology. But it's also the revolutionary Oscar Academy Award-winning effects. And these two guys, among others, at Industrial Light and Magic, Spaz Williams and Mark DePay, they really pioneered all the computer imaging techniques that have enabled us paleontologists to do what we do today. So it's unusual for, scientists to talk people outside of science per se, or academia, if you will, because these people really think and operate like scientists when you think about it. These people got us the tools for the first time, although conceived for a very different purpose, to be able to do these beautiful work that people like Steve Lautenschlager actually does. So yeah, I would just wanted to acknowledge the origin of the 3D and virtual paleontology to a paleontology in the popular conundrum like Jurassic Park. And to start, I want to talk about what 3D is. But first, yeah, what is actually a 3D model? So a 3D model essentially is your most basic geometry. Plain and simple, if you remember all your math lessons, you'll remember what this is. Basically, you are just representing a polygon, in this case a square, as a combination of vertices and coordinates, which can be expressed by binarial numerical values in both axes. Here, it's a more complicated shape, has more points, and you can see how each of these points or vertices have two-number coordinate according to the relative position in the Cartesian space. So, if we take this 2D approach and develop it within a third dimension, we can represent 3D objects through just, coordinates in three-dimensional space. So, in essence, what's a 3D model? A representation of an object by coordinates in all three Cartesian axes, that's points. They are united by vertices, which create essentially polygons which are adjacent. And these adjacent polygons can now represent a surface, which we call a polygonal mesh. And that mesh is the 3D model. And there's a lot of ways in paleontology to get a 3D model. But in my case, so I was a grad student. Nobody did back then a lot of 3D work. Heinrich Mallison, like I mentioned, he used CT scanners. CT scanners, either you touch somebody at a hospital that lets you work with their CT machine in between patients, which is complicated, or you hire somebody with a CT scanner. It's complicated. You can do the same thing with digitizing tools, which back then were basically laser scanners. Now we have far better and cooler portable scanners, but in any way, they are very expensive. So how can we get a model that is good, pretty, and cheap? So I use a technique which was introduced to me in college that has eventually taken paleontology all over, and that's photogrammetry. Essentially, photogrammetry, for those who don't know it, is just a technique that allows retrieving metric data from photographs. It's the same basic principle of cartography for stereo photographs. If you've used one of those in geo or cartography class, or it's the same kind of technology that lets your phone or camera take a panel just out of a lot of pictures that eventually match together. So, like I said, this technique of overlapping images mirroring what our eyes do for cartography is the basic origin of this. Later, that technology enabled to get a top-down bird view of an angle image if you had a plan, like a schematic of the area that allowed you to distort this picture into getting the actual bird view of the area. And it has developed in what we call now digital or stereo photogrammetry, in which we can take a lot of overlapping pictures of an object and get a 3D model out of it. So basically, it's taking pictures, like Brian mentioned, a lot of pictures of the same object, trying to get as much overlap as possible. This is the basic cheap way to do it, because the pros, for example, the Smithsonian Institution, they have rigs like this, where you can get a lot of cameras and lights to just push a button, bingo, you got a 3D model of your person, in this case, former President Barack Obama. And now we're going to the uncanny valley territory. This is the results of this. I find it really uncanny because it's actually made out of person, but it's just a 3D model of that person. They use this, by the way, just to print out his presidential bust.
Oh.
So yeah, this is the way you do it with money when you're on a budget. This was me 10 years ago. You can see how very basic my working was. I had the black fabric. These are diffusers for the lights that I used back in the day. I didn't have any really sophistication, so I just had, you can see the lights are in are in toilet paper. There's toilet paper actually there to diffuse the light and not have very bright spots. Ever since then, I discovered, thanks to Heinrich Mallison also, the cool ring flashes that let you take just the pictures and basically forget about it. And you can do pretty much anything with that kind of rig. Nowadays, I just take the same exact approach. For the moment, it's still working. And even in 2022, you can tell by the mask, you can still use the same protocol, and it works just beautifully. What you get from all these images is a collection. This is like probably the second or third model I ever did. I was just testing out the possibilities. This is from 10 years ago. That's actually a model, and I was, testing if different colored objects surrounding it would help the pictures align, etc., which they do, by the way. eventually, you get all these pictures. You get this to have the alignment of the different pictures, and you go through the different stages of the software which we use. Back in the day it was Photoscan, now we call it Metashape, but it's the same thing. So essentially, you get all the stages and you get a beautiful model with a photorealistic texture. So the thing is, most people, even today, will just want a nice and shiny 3D model and stop right here. Question is, now that we have it, are we done? Can we just, forget about it? A lot of people think yes, because it's just a shiny thing to show off how modern and how cool the new technique and how cutting edge we are. But it's far more than just that. It enables us to work in ways which was completely impossible before we had this technology democratically available and so affordable and accessible. And I'm going to go just, very quickly through some of the uses that we can have for this 3D technology. The first is basically just complementary illustration. Pictures are problematic, especially if the objects are large or too small. The camera lens has a distortion, the actual perspective has distortion, and even this exact same object can look completely different as, I don't remember if it was Mike Taylor or Matt Vidal who showed us on sbpow.com, their blog, that even the same vertebra can look completely different just with a very slight variation on the angle of the picture, which is terrible for two-dimensional analysis, by the way. 3D, on the other hand, does not have this problem. You can actually manipulate the perspective distortion to get it to 0 or to have as much distortion as you want for artistic purposes, but you can have very standardized depiction of fossils with it, which is a very good advantage for illustrating the morphology of them. Now, speaking of that, 3D geometric morphometrics. As we mentioned before, using 2D for these type of techniques, in case you don't know what 3D geometric morphometrics is you take points in an object, or in this case a fossil, which are the same for everybody, like, the suture between both maxillae, or the contact between the two first premolar incisives, in this case, or vertebra. You can have, like, the top of the neural spine, the diapophysis, the periapophysis. All those are the same for all the sample. So the idea is that we can use these 3D models to get a far better representation of the actual geometry we're analyzing than something that may have or may not have distortion perspective. Virtual restoration. Some fossils are broken beyond repair. They cannot be glued back together. Because the contact points are too thin to actually let the thing support itself. So we can just take those fitting fossils, have them together, digitize them, and get a complete model that illustrates this very well without the need to have the fossil in an unstable reconstruction. We can just have it separate and use a 3D model to ascertain the actual morphology. Same goes for fossils like this. This is concavenator. The fossil is, as most of this type of fossil sites in which you have slabs, fossils are just completely flattened by the pressure. They are completely flat, like post stamps. Huh. So what we did here was just fill in the gaps with known Allosaurus material and Carcharodontosaurus and Giganotosaurus material, and inflate it. So eventually we could have a look at what the skull of concavenator actually could look like. in 3 dimensions. Relative to the point before, and Brian was talking about this, yes, some fossils are fragile. And us paleontologists have butterfingers.
Huh.
That's more common than most people are willing to acknowledge. But let's be honest, we've all broken fossils in the lab, in the field.
Yeah.
That's because, I mean, just look at this bird. I have to update this figure because now I have a better cross section which goes by the sagittal plane, and you can see all the air inside. But you can see how thin this thing is and how easy it can be, you know, just to hold it, put a little more pressure with your fingers than you want, and broke. So 3D fossils not only allows us to not having to manipulate them, but if we make analysis and see where the biggest stresses are distributed among very fragile fossils, we can exhibit supports or holders by 3D printing, creating a perfect mirror surface in which the stress distribution is completely equal, because the contact surface is just as good as if you were making a negative cast of it. And 3D printing allows for making very aesthetic looking, non-intrusive display cases, unlike, you know, making physical supports, which can take a lot of work to get them to be efficient and non-intrusive for, you know, exhibit purposes. Soft tissue reconstruction. If we use, like Brian mentioned, the giraffe, but I've also been working recently a lot with some of my students with crocs. So if we get CT scans of crocs, we can segment the full meat of the animal and the skeleton and the muscles. So we can have a very good idea on how massive or non-massive these muscles actually were in living animals. So we can use all that information to apply those principles and reconstruct, and this is from an older work by Hutchinson and collaborators. And we can tell, looking at crocs, that these cross sections have been tremendously infra-estimated. They are very estimated on the very low edge. So these muscles would actually be much bigger. But we can tell that thanks to segmenting a lot. And by a lot, I mean like 50 or so animals. Most crocodiles that a student of mine has been doing for the last 2 years. And we are getting there to be able to have 3D models that enable us to really calculate mass within far shorter, far smaller intervals of error.
Wow.
And this leads us directly to paleobiological studies. So any reader of Vidal and Taylor blog, SVPO, probably knows about the intervertebral cartilage debate. This is something that I touched upon very briefly on my giraffe paper, but I have a lot more. The problem is information now, but I have so little time. Maybe I can get a student who wants to work on that and release a paper on it. But the thing is, how big is the separation between two adjacent vertebrae? If we look at a camel, we can see there's huge gaps in between vertebrae when they are in neutral position. I wish I had taken pictures of my camel, because I have a couple of virtual camels now, some from a different repository, but some I actually digitized myself from skeletons in the Sahara. And yes, it's true they have a huge intervertebral space, but we can figure that out with the bare bones. And how can we use the bone geometry to estimate that? Well, in the case of the paper for the giraffe, what I did was starting with these fossils, an adult and, well, I could call it subadult and a juvenile Spinosaurus nigeriensis. Basically, the process we talked before, every one of these bones had to be digitized by taking a gazillion pictures, some as few as 60 or 80, and the most complex maybe up to 500, 800 pictures. So that's a lot of processing.
Yeah.
And if we look at the zygapophyseal, because we have 3 points of contact between fossils, 2 zygapophyses and the centrum. The centrum is the intervertebral space we are trying to figure. But if we look at the other two zygapophyses, we can see that the soft tissue is very flat. It may make the bone, the actual surface of the bone larger, but it doesn't make it thicker. It doesn't have a wedge to it. So if we put those in osteological neutral pose, which according to the original definition by Ken Stevens is full overlap of just the zygapophysis, the centra don't need to be aligned, as was claimed later. This results in the juvenile in quite huge intervertebral space. Not so much in the adult. All in all, basically 20% of the neck length of the juvenile was air. Okay, yeah, some of these had to be estimated based on what came before and what came after, because the neural arches are broken, but is a fair estimation considering the good articulations we had. So, but what about taphonomy? Yeah, this is the question always in the minds of all of us. Is taphonomy really letting us have a clear interpretation on what we are studying? So that's why I went with giraffes. Giraffes are the only vertebrates that really have a neck comparable to sauropods in the sense that they are quadrupeds and not bipeds like birds. And they have ball and socket joints instead of having those saddle-shaped joints that birds have. So this is a calf of a giraffe that was CT scan complete. So we know how it was in articulation, and we can see that it has pretty big intervertebral space. This is the juvenile. Basically, you can see that the socket and the ball are not one within the other. And you can see this structure anterior here on C5. Can you see it? It's right on the right side of the ball of the centrum. So that's something ossifying that we can see on the CT scanner. The adult, if you have that in osteological neutral pose, is completely ball within the socket. There's very little intervertebral space. And surprisingly, because it could have been a different percentage, the juvenile also has 20% of its neck length made out of intervertebral space, soft tissue, whatever is in between vertebrae. The adult has almost no intervertebral space, less than 3 or 4%. As I mentioned, there's this weird structure here. Is it cartilage in the process of ossifying? Could be, because basically Matt Vidal and Mike Taylor found the exact same thing on dissecting a baby giraffe. And we can see this in museums all over the world. So we can say that, yes, bone geometry can help us estimate intervertebral space, and therefore osteological reconstructions based on 3D models are a useful tool to compare things like ontogeny, for example, in this case. And yeah, here's one of the slides still in Spanish. This is the other thing I was pretty interested in, which is how do sauropods mate? The most extended option, if you read Isles et al., no, it's just Isles, 2009, that paper basically claims that most dinosaurs used the same approach as most living reptiles, which is leg over back, which means the male gets behind the female and the leg goes, as it means, behind the back. So just a little phylogenetic context. We have mammals as our outgroup. We have turtles, which due to their caparazes have to mate what we could be calling a mount posture. We have tuataras, which do the sphenodonts, which do leg over back. We have other reptiles, which also do leg over back. And we have the sister group of dinosaurs, which are crocs, that also do leg over back. The most derived archosaurs within the dinosaur lineage, which are birds and theropods, birds have no tail, therefore they are not limited by it. So they have a pretty much different arrays of mating postures, but most of it is done by putting cloacae, or if they have an intromittent organ from behind, pretty much like turtles do. So a lot of like this Mark Hallett drawing from Matt Vidal's Sauropod book shows the sauropods in a leg over back posture, as does this Burian reconstruction, or these, I think this is Mark Whedon. And even these other reconstruction, there's a lot of leg over back in sauropods. So my question was, can they actually do this? Because you can see them in all these reconstruction, the male having always 1 foot on the ground, and the female is barely even squatting. How could that be possible? That was my question. So again, I went with Spinosaurus, and I did a little range of motion analysis to find out how big the abduction and protraction and retraction of the femur could be. What I found is the sauropod femur has an inverted L shape. Essentially, this means that if the abduction, that means getting the leg away from the body upwards too much, happens, what causes is the head of the femur to collide into what we call an osteological stop within the acetabulum cavity, which means that although these reconstructions are very, very impressive, there's a huge caveat on it. First, if you take a look at it again, the female has to be squatting a lot so the male can retain 1 foot on the ground, which is absent in most reconstructions. But there's another caveat here, and we can see it on the pubis. If we eliminate some of the elements so we can focus on the tail of the female, we can see that the pubis of the male is intersecting with the female's tail, which means that in order for the male to be able to adopt this posture, the female had to be far smaller, or for which we have, by the way, no evidence of big sexual dimorphism in sauropods. It's either that or the posture could not be attained without the male having its whole weight on the female's back, which doesn't seem to be the most comfortable thing to do for mating. So since this is not a good possibility for mating, that means that this posture was most likely impossible for a sauropod to perform, especially with more derived sauropods, which have an even longer pubis, like titanosaurs and titanosauriforms, which have huge pubic bones, which go even beyond their knees sometimes. I found this very funny because it's the exact same thing that happened with Tornier's sprawling sauropod. Tournier said, "Oh yeah, Diplodocus is a genuine reptile, so it must crawl like a reptile." And William Jacob Holland, which is one of my heroes in this, if you read the replies to Tournier, it's just so even mean in the tone. Like, with the help of a pencil, the powerful tool of a closet naturalist, Tournier proceeded to reconstruct the skeleton to the form which his brilliantly illuminated imagination suggested. Oh my, that's just so mean.
Oh.
This would totally not be appropriate today. But what I mean by this is that he actually took the cast of Diplodocus that they had at Carnegie Museum and tried to replicate the pose and found it to be impossible. Same goes for the leg over back. All the logic behind the leg over back posture for sauropods was, oh, all reptiles with tails do it. Sauropods must be doing it too. But it doesn't take into account that the croc, any reptilian pelvis, which is not a dinosaur, has a much shorter pubis, and the femur does not have the head at the top. It goes sideways because reptiles do sprawl, and sauropods don't sprawl like other dinosaurs. So out of fun, I tried to see, okay, what other possibilities exist? There would be like, a typical elephant-like position in which, the male rears up and has half of its weight on the female. But to do that, you could not perform a cloacal kiss, which implies that's the distance between the cloacae. So you can do the math on the size of the intromittent organ of a sauropod. And if the female laid down, the same problem happens. The distance between male and female cloacae is still kind of big, about a meter. But there was also this possibility, which has been suggested for thyreophorans, especially stegosaurs, to mate in a backwards position. Much like, there's a face in canid. Dogs mate this way in one of their faces, which is called the locked aim face. And here you can see that the cloacae could contact. So yes, that could happen. The cloacae could meet without the need of an intromittent organ or a quotation marks penis. But it doesn't mean this is the way they actually do it. It means they could do it this way. And finally, after all this dinosaur porn, I just want to say that this technology of photogrammetry also has a tremendous application in fieldwork. I can't show the most recent development I've done of this because I want to publish it, but I can show some examples of the past. This is the first time I tried to do it. Basically, everybody's been working with footprints, with dinosaur ignites, has been doing the photogrammetry for decades, ever since the late 90s, before we even thought about using it in bones. But to my knowledge, not a lot of people have used it for bone quarries. So this is El Atance, which is a Triassic location in Guadalajara, Spain, not Mexico. And if you see the site, this is from the 3D model. We had a huge wall, so we couldn't take actual top-down pictures. Nowadays, you would do it with a drone. But two things, drones were not as common back in the day. And two, in Spain, you need a special permit to fly one. It's a pretty bad thing to go through. So we did a photogrammetry of the site just the final day before we made the jackets. We have like 3 marine reptiles here from the Triassic. And we could take this to make a actual map of the quarry without the need of, the traditional net of elastic 1 meter per 1 meter square, which also has its own problems when it comes to perspective and distances. Nowadays, what I will be doing, this is the day we opened a quarry. I will try to take one photogrammetry scan of our digs every single day at the end of the day, because that way we can evaluate how the dig has progressed, which it has very big implications for sites, for example, where we cannot leave any fossils from one day to the next. Some of our fossil sites are within recreational areas where people will be camping, and there's always the danger that they may grab a fossil, so we have to close the dig every day and grab the fossils out before leaving them, especially the mid-sized or small-sized specimens. So if we want a complete quarry map, we can just put together all the different scans and see the evolution of the excavation and have a very precise location on each of the elements of a bone quarry. So I have a lot of more to say about fieldwork and 3D, which I hope to publish later this year. I'm working on it, and as well as many other things. But for now, there it is. Here's some uses of 3D, and I would really love to engage in questions because that's what I'm here really for. So there you go.
Amazing, awesome. Hats off to you. Unbelievable. There's lots of questions in the chat. I'm going to jump in as a host and moderator and ask my own questions first. And so membership has its privileges. The very first question is, was that a brachiosaur dorsal vert spinning around in the early part of your presentation on the black background when you were emphasizing tissue paper? What was that specimen?
Was it spinning, or was it in an FEA analysis?
It was on the rotating table in the black.
Oh, no, that's not Brachiosaurid. That's a replica of a dorsal vertebra of Saltasaurus.
Okay, because it looked really small and wonky. Macronarium, we'll give it at that. It was I've seen Saltasaurus, and I was trying to figure out what the heck is that, but I was thinking anyway. Thank you. Second thing, you've been at the Carnegie. Let me rephrase it. I find it challenging when I have to put away bones on bespoke receptacles because I don't know which end goes where. Is it the left or the right? How does it go? And if it doesn't go exactly right, I've broken more bones trying to put it away in these aesthetically pleasing bone holders than I ever have on flat shelves like at Brigham Young University or the old AM&H. So you're advocating people do things that break my heart. But they look great, and if you don't need to use the bones, sure. But for me, it's heartbreaking. What are your thoughts on that?
My thought is one thing is an exhibit support, and one thing is a storage support. So the exhibit support has to maximize the support of the fossil without having it being on a delicate position, while on the other hand, it has to let people see as much of the fossil as possible. If it was up to me, say, skulls are their own beast, and each one has to be treated its particular way. But thinking of vertebrae, I will always advocate for, if possible, a vertical support. I mean, the way it would be in life for exhibit purposes. Once they have beautiful shells for that in the Field Museum for Brachiosaurus, and I've seen them pretty much everywhere. The idea is you have those, but if you get also A and B shells that fully enclose the fossil, basically what you could do is just have that in exhibit, and if you have to transport it or you want to see the underside, just fit one of those two halves.
But it's
never fully supported too.
With
the sauropod, it's never that easy.
Yeah, that's where I don't care about the rest of the animals. They can do what they want. I care about my sauropod studies, and those drive me bonkers. And the clamshells are the worst because I got to bolt them up, flip them over. It takes me an hour to move through a couple verts versus just flip.
Well, first thing, that's why you do 3D models for it. So we no longer have to really go and disturb the fossil, except for, very tiny things that we cannot make with 3D yet, like fine texture on the bone, like insertion marks that are very subtle, that you can only see, with your light very low and really with a magnifying glass. We can get that with the most micro CT scanners, but you cannot get a 3 feet vertebra into a micro CT scanner.
So, but go ahead.
for one that, and for a second, I always think that for those clam supports with a lot of close, I feel that when I have to turn them around, as long as I have two or three screws in opposite directions so it doesn't open, that's totally fine. Most of the time, I
But if I
get away
wanted to
with
run
it.
back, I've got the right side up and I'm looking at it, and then I don't remember what the left side looked at. I want my cake and eat it too. The problem with 3D, I don't know what's been restored, and I didn't see any questions about that. But how do I document, like, if I'm looking at three-dimensional scan data, how can I tell where it was imagination land versus restoration on a 3D scan without touching the bone?
Okay, so here's several approaches you can do with that. And it depends on what technique you used for making the model. If you use a CT scanner, dead on. I mean, unless you have very dense infill for restoration, which was never ever done because you want the thing as light as possible. You can tell it apart very easily. So you could potentially, and that's what I do because I do a lot of CT scanning now. I try to reconstruct the sediment separate from the actual bone in different colors and different models. So you can have the whole thing together as it is in the real life, and you can have just the actual bone. Yeah, and like those
Yeah,
those are Larry, right? Larry Whitmer.
I just CT scan these. I grabbed Larry into this project. We should chat CT. I use spectral scanner from Philips now, and you can see that restoration, that break in the bone in the CT immediately. You're like, oh, I didn't know that externally. I had no idea it was fractured that way. I thought that was pretty cool.
Yeah, that happens a lot with historical specimens, which is a pain because they used to paint them in the same hue. So it's very difficult to tell apart. Nowadays, you use another color, so it's very easy.
You may not know this, but some commercial folks grind up ribs to put it in their paint so you can't tell externally that the bone was actually plaster on the outside. They'll put a bone skin on it.
I know. Especially I've seen that from Moroccan specimens. This is a very nice thing. In a fossil shop recently, I saw a Spinosaurus vertebra, and this was great. Yes, that was a vertebra. It was a caudal vertebra, and up to the base of the spine, it was all good. But the fossil dealer thought, nah, I'm not gonna sell this. So he took a rib and placed it in place of the neural spine. So you were following the laminate, and all of a sudden they would disappear into this rib out of the blue, and it was grinded bone. So I was like, because I normally don't bring things up to people when they have this type of things. My former advisor, they were terrified of. He would be like, oh, that thing, it's not worth what you're saying. Oh, that, I would never do that myself because I'm maybe too nice, but yes, they do that. Commercial fossils are a pain for that, especially. And I was going to say what I do with photogrammetry of especially historical, and by historical I mean pre-mid-90s. Some were, and even some current fossils are still doing that in some places, but most of people are now using different colored infilling, or no infilling at all, and just leaving the cracks open as they are. So what I will do, I'm gonna try to retrieve a figure. Let me see. I think I've got it here. So this actually this is going to be a figure of paper I've been working on for a long time. So spoiler alert.
Love it.
It's opening. Yeah, it's a Photoshop file, so it will take a couple of minutes. But what I will do is I will gather all the information on the actual fossil if you can actually see it. So, the good thing of photogrammetry is you get the actual texture of the bone, the color, and you can kind of follow it. So what I will do in my own textured files, what I will do is essentially just, I'm going to screen share now. I will paint what's real in one color and what's been restored in a different
Oh,
color.
how beautiful. And how much time that requires, though.
Yes, I mean, say for example, this is Amargasaurus, and there's a lot of reconstruction in the centra of the dorsals. And yeah, there's this, for example, is not restoration. This is just infilling, uh, basically matrix. But there's some restoration on the neural spines, which is fair because you have the preceding, which is complete, and the following, which is complete. So yeah, this is not too crazy, but it's not real either. But yeah, that's the way I think it's better.
That is
Strong contrast
amazing.
colors.
Amazing. Time. So again, hats off to you. Kudos. You're a researcher's researcher. Thank you. Let's get to the questions over here, but I do want to come back and I'll make a quick comment on our good friend Holland. His rebuttal actually caused Archduke Ferdinand waded into the fray and had an opinion on the Diplodocus walking, and he, of course, sided with the folks across the pond from the U.S. standpoint. He did not side with Holland, but I think that's probably the only time an archduke had an opinion in paleontology that was shared across the world was because of the international incident Holland's just vicious response engendered. It was great. I loved it. All right, so we got some questions here, a bunch of sauropod neck questions. What do you believe the next? Oh, by the way, we're coming up with 5 minutes left. I want to be respectful of yours and everyone else's time. Do you have a few minutes? Because we're at the questions, and I just want to make sure I don't run out of time on your end. So
I have a full day.
okay. What do you believe the necks of sauropods are used for compared to those of giraffes? Were they used to compete for mates and territory, or just to aid in browsing vegetation?
So that's a very complex question because it has multiple answers. One could say that necks evolved due to something, or they were an accident, because both are possible. You can have sometimes development does these things, and it pushes an organism in that one direction, and it's dull or slow, quotation marks. When the organism wants to go back, it's very hard. Even the shortest necked sauropod, which is Brachytrachalopon, has a very long neck for any vertebrate standards. So reducing the neck would be extremely hard. So part of it might be just, they evolved in a certain way and they couldn't go back. But it's true, long neck, extremely long necks evolved many different times and in many different fashions, either by multiplying the vertebrae in the neck or adding vertebrae from the back into the neck, which are two different processes. And but the overall goal was the same. So why a long neck? Probably a lot of different reasons. We don't know for any sauropod. We have a bunch of Camarasaurus specimens. I think it's got to be the most abundant. Maybe next to Shunosaurus. Those two have to be like the most the best well-known sauropods from a bunch of specimens. And we have not a very good idea on whether there was any sexual variability on their neck length. It doesn't appear to. So could it be used for mating competition as it is in giraffes? Why not? We don't have a lot of evidence of broken cervical ribs, so that's negative evidence for, necking, at least in the style of giraffes, or any necking at all. You could see that there might be some accidental pathologies, but it doesn't mean it didn't happen. Maybe it was more gentle than it looks. Then again, eating access into different food resources, that's a no-brainer. Obviously, it enabled them to go further without having to move than other animals the same size. So that's obviously one of the possible adaptations. Then there's also one thing I noticed: most sauropods cannot drink water without ambling like giraffes. So maybe one of the reasons for the extreme neck elongation of some sauropods was actually to be able to get the head to the ground and drink without the need to be ambling and be vulnerable to predators. Maybe that was one of the drivers, especially for short-limbed sauropods like diplodocus, which have tremendously long necks, but they were not like brachiosauruses, which are trying to to go up by making the leg longer and the forelimbs even longer. So there's a lot of reasons they could be, and I think each clade, each group, and maybe even each species use the neck in a particular way which was advantageous for it.
Love it. And you answered the next question, which, how's your opinion about the neck posture of Diplodocus? I remember indicators like micro-wear and muzzle shape suggesting it was a low browser.
So Diplodocus, Diplodocus, my good old friend. I've been looking forward to get my hands on a Diplodocus complete specimen, or one which is complete enough, especially sacrum to head, that I can settle on what happens with its sacrum and back. Because if you remember my 2020 paper on the angle of the sacra, Diplodocus has wedging in the sacrum. A lot of sauropods, most sauropods, except for the most basal, do have this. But a lot of them create a counter wedging in their dorsals. So the that typical sauropod image when the back is making a nice arc, like your typical Flintstones or Sinclair oil sauropod. That type of back is real and happens in some sauropods. Haplocanthosaurus, for example, is one of those, and Nigersaurus would be the other sauropod which has that type of feature, and a lot of Titanosaurs do have that. But Diplodocus, not sure. Just some mounts do seem to have overlapping vertebrae correctly articulated that don't go down, and then you have the Seckenberg Museum specimen, which is crazy going up. So I really want to get my hands on one and test the hypothesis on that.
We've got a Barosaurus we're describing, which we should loop you in on, which is caudal 22 through cervical 8 in articulation, complete pelvis, mostly uncrushed.
That's the one I've been seeing around in Instagram lately.
Museum of Ancient Life.
I think it might be.
Lehi, Utah. It came from the same quarry as AMNH 6341 and from the same quarry, but 3 meters or less away from the material that's coming out that Thomas Lindgren is excavating from Bone Cavern Quarry. So it is so we've got 3 specimens with pelvic material, all from the same taxon, all from the same quarry, that would be ripe for study. And the Museum of Ancient Life is actually accessible, and it's not a commercial specimen, and it's not behind glass or tucked away in the annals of the AMNH. So you can get to
so it would be. It's ready. It's available for research. Those specimens.
Yeah. So
so
we should chat offline about that. But yeah, we've got we're proposed. We've asked Treebold Paleontology to scan it and then make a cast out of it so we could resell it. But my thought is, for research purposes, let's scan that specimen. There's a bunch. Yeah, so there's a lot of fun things we can talk about, but I interrupted you. You were going to say, despite all of that, and then I cut you off. My apologies.
Yeah. Oh, never mind. So what I wanted to finish is, yes, Diplodocus has short limbs, so that means the neck is lower by default, just by having shorter limbs than most, say, something like Spinosaurus or Camarasaurus. So there's the dentition, the type of dentition of the, front, the muscle shape. That type of dentition has been shown to be not the best for very coarse vegetation, unlike Camarasaurus teeth. So whatever it was eating, it was softer plants, probably not conifers. But the height it could actually do it, I mean, it could lift the neck always. I think one of the things about the neck debate, which makes it particularly sterile, is that it supposes that the necks were stiff. So they had like this neutral pose and they couldn't go beyond that, which is not true. Giraffe necks are extremely flexible. And sauropods probably, like in the figure in your background is showing, they were probably just as flexible, especially those of diplodocoids in which the cervical ribs are not fully ossified. So to answer the question, whatever it was eating, its range of motion probably enabled it to go very high because it has a very long neck, and also very low. Probably Diplodocus was more specialized than Camarasaurus. That would be my thinking.
What about Mamenchisaurus?
Mamenchisaurus, unfortunately, I've never been able to study them except for that overwhelmingly present cast of the original M. youngi specimen, which probably is like a third or fourth generation cast, which has a lot of blurry details. So, it's very complicated for Mamenchisaurus because their necks are so unique. In the way that they have so many vertebrae, their dentition is very spatulate and broad, but their neural spines are so short, which means very weak lever. But on the other hand, they are super long, which means a very long anchor for a dorsal neck ligament. Oh, wow. I wouldn't dare with Mamenchisaurus because I haven't studied them myself.
I love your humility and your honesty. It is refreshing. You're not just making stuff up. We're going to shift to another question along these same lines. Any thoughts on diplodocids and possibly titanosaurs standing on their hind legs when encountering large predators?
I mean, first things first. Could they stand on two legs? Yes, totally. All sauropods, even the most front-heavy sauropods like Brachiosaurus and Giraffatitan, have center of masses far more posterior than current-day elephants. And modern-day elephants stand on two legs without any sweat. They can stand on the front legs and on their hind legs. I pretty much doubt any sauropod could do a handstand because exactly the weight is far too posterior for them to do that. But essentially, a sauropod is a biped that became a quadruped. Unlike other animals, which are either quadrupeds that have been always quadrupeds, but sauropods come from bipedal ancestors, and that remains in their overall construction, which means, yes, they can stand on two legs. As for the predator scenario, could they do it to look bigger? Yes. Are they exposing their bellies when doing that to attack? Yes, as well, but so is the predator exposing itself to having a 30-ton animal fall on top of it. The question is, could they do it? Yes. Did they do it? Nobody knows. Somebody research a time machine and we'll be able to find out.
Though I just want to go forward and get the next winning lottery tickets, and then we can fund everything.
Exactly.
Time machine. What do you think about tails as weapons and the sound barrier, the old Mirvold and Curry 98-ish paper?
So I have a big critique on. Actually, let me. I'll be right back.
You guys gotta love this. This is amazing.
Aside from science, I also like whipcraft.
Okay.
So I know a lot about the subject. I've won a tournament in Spain, so I know my way around whips a lot. So I know how to use them. And last year there was this paper in which they did both a critique from the that was Conti and collaborators. I've talked with Simone Conti about it a couple times. About this, I disagree with their paper. In my opinion, it has two flaws. The first one is, yes, it has the material property analysis in which they claimed that the tissues that make up a tail would break in a supersonic stress. Thing is, bullwhips are made of skin. Okay, yeah, it's leather, but still skin. They go through a lot, and they're dead skin, which means some parts have to be replaced. And I found that for once, for skin they used pig skin. Pig skin is not the best skin to compare it with. It's great to compare to human skin, but human skin you don't make unless you're Buffalo Bill. You don't make hide from from human or pig skin. How many of you have seen leather pig jackets? Nobody does it because it's very frail. It really disintegrates. It's not good leather. So I would think that, I mean, they don't make them out of elephant hide either, because elephant hide is just so massive. So, but if you compare that with crocodile hide, which is far sturdier, you can make leather objects out of it, not a whip. But in any case, they tend to use kangaroo leather, for example, which has very elastic properties. And that's for one. I don't think they use the best analogs for comparison in some of the soft materials. And on the other hand, they did this very cool and elaborate simulation of the tail whip. Here's the thing. They should have tried that with an actual model of a whip first. Why is that? Because we know that whips do crack. They break the sound barrier. And like I said, I know how to use the whip. So when I saw the video of that paper, I thought to myself, if I do that with an actual whip, it's not going to crack. Or it will crack maybe one time out of 10 by sheer luck. If you look at the graph of that paper, you will see that the speed goes up and down, up and down, up and down, up and down. Whereas if you look at Nathan Merville's paper, speed goes like this. Why does one go up without any peaks and valleys? And why does Conti et al. Have valleys? They have valleys because that motion they did for the model creates a lot of waving, which essentially is energy dissipating away from it. That's why its speed does not grow incrementally and has peaks and valleys. So my main critique is that the motion you use on a whip is very important. Because you give a whip to some, random person who's never seen it or used one, they won't be able to use it. Believe me, I've been there, done that. So yes, I think the analysis should be done, but right now I think the parameters and the motion program by Merville is a better motion to get a crack out of a sonic boom out of a diplodocoid tail. So right now I think Merville's hypothesis is not refuted, if you ask me.
Wow, good to know. You heard it here second. Conti's paper, I remember when it came out, I was like, all right, cool animations, must be true. But I am not a whip expert. I don't dabble in whips, nor do I play one on TV.
Imagine this whip is the last 15 feet of the tail of Brontosaurus. The lack of broken bones in the tails that we find suggests the tail was not impacting its enemies. But what it could have done is this. Creating thunderous cracks, the tip of the tail exceeding 720 miles an hour, enough to scare any enemy away.
So I'm so glad to know that when I have whip questions, I found the gentleman that can solve my answers. Next
You can ask Mervil too, by the way.
Oh,
Mervil
yeah,
also does
I actually
whips.
reviewed that paper. I was one of the reviewers on it,
Of
and
the 97 paper?
yeah, I caught a math
Oh, wow.
error on it because their original math had it snapping with every step. So I'm not a math guy, but I was really proud to find that and say, "Hey guys, I think you might want to look at this again." So I was, yeah. My very first correspondence with Nathan was he made a comment in like a chat in the old school dinosaur mailing list. I drive a Hummer as a field vehicle, and I didn't realize who he was, the chief technology officer of Microsoft at the time. And I said, "Really, a Hummer?" And he's like, "Yeah." And then I looked him up. I'm like, "Yeah, you probably do."
Indeed.
I remember from the documentary on Dakota, the Edmontosaurine mummy, that the discs between the verts added an additional meter in overall length to the skeleton. Does your data support that?
So here's the thing. We're in my analysis, I was looking at ball and socket joints. Most of Dakota or any hadrosaur, except for the very short necks, are flat vertebrae. And flat vertebrae are different than, for example, I have assembled a lot of sauropod tails, and all sauropod tails have a pretty thick intervertebral disc. Not so much for the ball and socket, but just for the amphicoelus or platycoelus, the flat surface vertebrae.
And what about going back to the bipedal motion? What about blood pressure problems, or when they went to jump up on their hind legs, or even raise up or go to drink?
So here's the thing. We can speculate all we want about the size of the heart, the thickness of the aorta, or the carotid. We can speculate all we want about accessory valves. Doesn't matter. To me, it's like talking about the sex of the angels. We can't know unless we have fossils of it. So to reply the question, I would say whatever they did, it worked. Because we have extremely long necks for a lot of sauropods, evolving multiple times for 150 million years. So whatever they did, it just worked.
And that's a great segue into the next. There's three questions that all talk about the similar concept, which is, how does your work on sauropod anatomy and biomechanics tell us about sauropod ecology, about the role sauropods played in Mesozoic ecosystems, and about their lifespans and how they got so large and why?
So the work I did in my thesis and the range of motion and biomechanics analysis basically can tell you the main thing it can tell you is negative evidence. That is, they could do this and this and this, but not that, or that. So we can basically take apart a lot of things they couldn't do, have a spectrum of things they could do. But the question on whether they did them or not, like I always say, that's up for the physicists to find a time travel machine. But there's no evidence that they could not do it. And if they could do it, maybe anecdotally, maybe a normal staple of their behavior, but they could do it. That's what it provides. It provides evidence to say, if you think, oh, could sauropods be doing leg over backs? They just couldn't. So there it is. I mean, you can use that to negate certain aspects of the ecological interpretation of sauropods, but you can never, and this goes for biomechanics, or it goes for isotopes, or any kind of analysis, tooth wearing, micro wear, and anything. You can just use that to say, this is how it worked. That's all the reasons it could have happened, but we cannot know exactly which one. And it's a caveat of paleontology we have to embrace and just accept.
So speaking of not knowing, where did it go? It just moved. How does your work about variation? So where did I see that one at? What are your thoughts on the extent of intraspecific size variation in sauropods?
Well, That's a good question because I just been working on some of that on Meteorosaurus lately. We have a very big sample of Meteorosaurus. It's a very common sauropod, and we have the samples in all size and shapes of Meteorosaurus. And the good thing here is that we can do histology on them. Histology is very good at telling us how mature a specimen was, independent of its size. So what we're trying to do is to figure out, okay, are there small adults, or only the very big animals are adults? The most probable answer is that sauropods, like most vertebrates, I mean, you just have to look at people. There's the tiny people like I am. There's the hobbits like me. There's the Michael Jordans and beyond. The Bolaji Badejo, who played the alien creature. So, and even people which are shorter than me, and then you have all that spectrum. So from I like the example of twins. You got your Schwarzenegger, you got your DeVito, both humans, and probably the same was true for sauropods, even within the same species.
Love it. It's the 5 standard deviations. You're going to find them. We have 3 supersaur specimens. All are about 1 meter apart in length. That's the average. I mean, if you got 3 big animals from 3 different quarries, all coming up with the same size, okay. Now, what does a really long one look like? That's terrifying to consider.
Exactly.
And how do we know if you find a small one? We think we found characters recently, as a random aside, in the tail at least. So different. All right, last couple questions here. Do you think Jurassic Park got rearing right with Brachiosaurus in the original?
You mean, there's a very cool paper by Heinrich Mallison in which he tested that the Jurassic Park posture is not the best way for Brachiosaurus to get to rearing, but it could rear. So the answer is yes and no.
Like all answers we deal with. And then same concept. There was a paper last year talking about hippos versus elephant-like walk for the sauropods. Based on your sauropod anatomy studies, do you have any thoughts on how they would have walked? More hippo or elephant-like?
So I've never done a lot of focus on walking and on appendicular for locomotion purposes. I've done more that with the tail. Whatever they did, I can pretty much say that it would not be like a rhino, like a hippo, or like an elephant. And why is that? Because neither of them have big tails. The powerhouse of dinosaur locomotion, except birds, is in the tail, the caudofemoralis longus muscle. So basically, while most mammals, if you look at a mammal pelvis, you can see that the anterior end of the ilium is very developed. And only some sauropods have a very developed anterior end of the pelvis, by the way, those which tend to reduce the tails, mind you. But, so we can think of, just like with cars, there's cars which go by propulsion, and there's cars which go by traction. A sauropod is a propulsion model in which the tail basically pushes the animal, while a mammal pulls for locomotion. So it's more of a traction car. So basically, that's the way it is. That they would be different in locomotion mechanics. That's for one, and for another, whether they ambled or not. That's a very complicated question. Not even the people working on footprints, which I think have the best evidence at hand, which is the actual product of the animal walking, can really have a very definitive answer. So my answer is like neither, and of which of them would be more similar, even if it's not exactly like them. I'm not sure we can really tell. I think Ken Stevens, I heard him once say that it works either way if you have the parameters right.
Yeah.
So it's very complicated.
He just walked us through that. It's funny you mentioned that paper on his tracks from Switzerland or somewhere he was at. And you can fit, depending on all the variables, you can get all of them to work just depending on the speed and the heights of some things. It was crazy. Um, The last question, unless anyone's got anything they want to raise their hand for, is not about sauropods. So I left it till the end because I'm not really excited about theropods, but it's an interesting question, which was when you recreated the concavenator, you mentioned using Allosaurus material and some other critters instead of Eocarcharia or one of the other more, I guess, phylogenetically close beasts. Why would that be? And my guess is because you had access to the material, but I was curious to see the answer.
So that's the first one, and it's correct. You got it, but there's another reason too. Allosaurus, because it's basically like the best known allosauroid, so it's actually safe for Acrocanthosaurus. I think it's the only one with a full skull, and of which actually we have beautiful articulated specimens and multiple specimens. So that's one of the reasons. The other reason is that, for example, Eocarcharia has very little skull material, basically the maxilla. And we already had the basic outline of the maxilla of concavenators, so it was not an issue. And as for the others, yes, that's exactly the reason. I had access at the time to Carcharodontosaurus and to Giganoto, but I didn't have access to Acrocanthosaurus, which would be the other prime candidate with, a skull complete enough.
You can only work with the stuff you got. So
exactly.
What similarities have you identified between giraffe necks and sauropod necks? And should we be cautious when using giraffe necks as analogs for sauropod neck function?
Most sauropods have feather-relied neck vertebrae. In particular, Spinosaurus is a very primitive sauropod. We have the vertebrae broken in half due to excavation, and it's far more massive than your average, Diplodocus or Brachiosaurus or any titanosaur for that matter. So in the particular case of Spinosaurus, it only has like these large excavations on the centra, which are foci more than actual pleurocells or pneumatic foramina. So it's not invaded by air like other sauropods. So it would be far heavier. In that regard, we can compare them in a fair condition to the giraffe. But also giraffes, the neck vertebrae, they're not massive. Just like an elephant's skull is full of air, the amount of actual mineral bone in the giraffe vertebrae is not it's not a massive thing like a Titanosaur osteoderm, which we have very densely packed bone. It's not air what it has, but it doesn't have like all the bone completely mineralized. It has more trabecular kind of bone, which is the same we do. Like a lot of our limb bones are full of trabeculae. They're not solid bone. They're not completely solid. So the neck of a giraffe is not as heavy as you would think, on the one hand. And to finish this, I would say that basically the pneumatization, the invasion of air sacs into the neck vertebrae, that is the most different thing. Aside from the other stuff, like some different muscle arrangements, which coming from two different languages, but most of it, vertebrae change very little. And the overall architecture of them, they even have processes where the cervical ribs of sauropods are, and they hold insertions for muscles that may or may not be homologous. There may or may not be the same muscles. That depends on embryology and its studies, but the function they perform is the same. They have bone socket type of joints. They have projected pre-zygapophysis, unlike other animals which have projected post-zygapophysis. So from a purely morphological and mechanical point of view, they are more similar than a bird's, for example.
Great answer. And I remember I had at one point in my house a neonate giraffe neck and the first couple thoracics all the way through a bull. I had 5 necks laid out for almost a month in my living room. And yeah, my wife eventually didn't find the odor particularly pleasant, and the beetles that didn't all die when they should have died roaming around.
Yep.
But what an incredible experience to note that. And I'm mad at myself because I didn't ever think about the gaps between the juveniles that had been, this was in 97 or 99. So I could have seen this long ago and I missed it. So that's why they call it research. Search again,
Exactly.
or in this case, I'll go look at what you did.
Would sauropods have used their necks defensively against theropods, or would they have kept their necks out of reach of jaws and teeth?
Yes, I would think that if sauropods were to defend themselves, they would use the tail, as most reptiles do. And modern reptiles, they fight with their tails a lot. If you lose the tail, yeah, you can have some problems, and not as many as if you are caught in the jugular or in the carotids. You can bleed yourself to death, while if you lose a chunk of the tail, it's not nearly as bad. And also sauropods, they could twist their head around, so they could actually see what they're doing with their tail.
So could they use their necks to look behind them as well as in front to detect approaching predators?
That's assuming there's pack hunting, which is another debate in paleontology. But yes, they could. The only issue here is how fast could not only turn their heads and necks, which can be kind of approached with the inner ear. Those sauropods with more reduced semicircular canals in their inner ear probably couldn't do as fast head and neck motion. Not because they couldn't do it from a mechanical point of view, but because their own sense of equilibrium would be like completely out of place, and they probably would feel dizzy if they twisted their head or neck too fast. They couldn't process it as good. And there's the nerve question thing. We know that there's this nerve which goes around the aorta. I was talking with some friends yesterday about this, and with the very long neck, the nerve response is, the nerve transmission is, doesn't matter the size, it's just as fast. The longer the nerve, the longer it takes for the nerve impulse to go up and down your brain. So it's not like those old cartoons where, which was the Thagomizer author. I don't remember the name right now.
Gary Larson, Stegosaurus?
Gary Larson. When you have, the caveman poking a dinosaur and two empty vignettes and then bam. That's how long it takes. But it would be a fraction of a second, but longer than in a shorter neck. So you have to take all those things in consideration. Yes, they could do it. They could turn the neck and head around to see what's behind and be able to know what they're doing with their tail. Maybe they also, because maybe the proprioception they had of their tails was not as good, because, the distance those nerves would have to travel would be a little delayed. Not like by a huge chunk, but it would be certainly some microseconds delayed next to other animals. So potentially, yes, they could do it, and it would be preferential with the tail rather than with the neck.
Would the relative size of the head compared to the neck and body be a factor?
Yes, this is not as talked as the postcranial pneumatics, but the head of most sauropods, you've seen the nasal cavity. For one, that's huge. That's a huge cavity, and that's all the big macronarians and all the primitive sauropods like Mamenchisaurus, Turriosaurus, that have these huge noses. All that's filled with air, which is very light. In addition, sauropod skulls are ridiculous. Most sauropod skulls, because there are some exceptions, but the big majority of them are extremely delicate and lightweight. That's why you don't find them that often, because the bones are so delicate that just like the tip of the tail on the tip of the fingers, they just are washed away before the own current burying the sauropod can just detach those bones and take them away. That's why we have so few complete skulls for sauropods.
That enlightening.
Yeah.
Could sauropods have developed sore throats? And if so, how severe might they have been?
some particularly immune animals like crocodiles. Crocs can, be beaten up from battle with another crocodile and get into a stagnated pond, which should be full of microbes, and still just rest and recover there without getting sick. Crocs are amazing for that. But so I believe that, but even crocs get sick. So probably sore throats, yes, that probably happened to sauropods too. Some sauropods, especially at the end of the Cretaceous, they lived in a world where there were seasons. There were no seasons in the Morrison Formation and most of the post-Pangea continents, the Gondwana and Laurasia. They were far more hot and tropical than nowadays. But we know there were seasons by the end of the Cretaceous, and there's sauropods in relatively high latitudes. We have them in Antarctica. It was not as cold as it is today, but it was far cooler than the Ecuador. So yes, probably they got those kind of disease, and probably it was as unpleasant for them as it is for us.
All right, everyone. Thank you so much for spending time hanging out with us, sharing such incredibly cool videos, and answering the questions in great detail. Truly appreciate it. We would love to have you back, especially when your next paper comes out. Bring more cool stuff. Thank you all kindly. Good luck, good hunting, fly be free.
Dr. Brian Curtice is a dinosaur paleontologist best known for his research on sauropods, the long-necked giants of the dinosaur world.
This animal is near and dear to my heart. This will probably be the name-bearing specimen for our new species of Diplodocus. And I dug this out. I'm not even humble bragging, I'm bragging. This took a long time to get out of the ground.
He has collaborated with scores of the world's leading paleontologists and has worked in hundreds of natural history, science, and dinosaur museums around the world.